We're from Grand Rapids, Michigan, and this is Sand Piles and Software. Alright, so all of us here, I'm assuming, are electrical developers, and whether we work alone, or we're going to install teams, or we're going to really big teams, we have a tendency to kind of do things in a certain way, in a very visual way, such that our past habits often predict our future behavior. So if we're tacking stuff on today, we're probably going to do the same approach and just tack stuff on to our software tomorrow. If we go out writing tests today, we're probably going to go out writing tests tomorrow. If we go about refactoring today, we're probably going to go about refactoring tomorrow. And if we don't do any of these things today, then we're probably not going to do any of them tomorrow. And as unpredictable as software is and can be, we're actually quite predictable in how we go about doing things. So if we look at our own behavioral patterns of how we produce software and make decisions, we pretty much make the same decisions all the time. This leads to a sort of regularity that we have in our own process for building things. So we may not know what all of the minute details are going to be along the way, but we know the general approach, the general flow that we're going to do. And sure, there are times where we kind of get knocked off course or an idea and try something different. We kind of break away from that regularity. But just like knocking an pendulum, as you walk by, it's going to fall back into kind of naturally. But when we iteratively kind of go through this process of building software, making these decisions, and we do it again and again and again, day in, day out, and based on all of those micro decisions that we make, we end up, kind of our software emerges. We produce something. It might be something fantastic. It might be something horrible. It might be something that's going to thrive moving forward, or it just might be something that's on a death trajectory, whether it's going to die tomorrow or going to die in a year. And while we're iterating, making all of these decisions, there are always opportunities for feedback, and for us to pay attention to that feedback. My favorite is kind of primitive gut feel. The kind of get this emotional reaction to it does or while it's approval. Even before you dive in and understand what's doing. Some of this is structural, some of this is conceptual. Once you dive in, you may find that stuff that you thought was really relevant. Structurally, actually, it's really gross, and it has a lot of visual complexity kind of baked into it. Then there's the peer review. If you do parenting, or if you just do code reviews, or if you just have someone review your code on GitHub, that is a huge feedback mechanism. And then, of course, the tests, the automated tests. If you're going about or trying to write a simple test around really complicated behavior, you're going to feel some pain there. And then there's a million different metrics that we can collect. There's a lot of programs. Since Ruby's not static, we get all the static analysis of different languages. But there's enough out there. And I'm sure there's a bunch of other things that we can collect feedback on. And the problem isn't that there's not enough things to collect feedback on, or that we don't have feedback. It's that we actually don't pay attention to it. Kind of our intuition tells us to do something different than what we're doing. And if you've seen this before, you'll probably know that all the lines in the middle are actually the same length. But it doesn't work that way. We kind of have to force our brain to be conscious of that, and we kind of have to tell it. They really are. But our intuition kind of steps in and it does the least amount of work possible to say, like, oh, the bottom, that's the longest. The middle one, that's the second one. The top one, that's the shortest. That's not actually true of our experience. So when our intuition fails, especially when we're in code, we think we're making an isolated change somewhere. So what we intuit is that, we're just going to tack something on here. It won't be that bad. We're just going to break one small window. It's negligible. The overall impact on the system. But that's not really true. Software doesn't work that way. So what often happens is, the picture on the right, we have a lot of broken windows. Real quick, there's not a whole lot of code slides in this talk, so I'm just going to do one example now and then one example later. And here we're just using a simple array data structure. We're going to shove some records in it. And this happened in an actual project where the team actually had built the system before us, had kind of taken this approach. And they said, well, you know what, we're going to fill that record set with stuff from Solar, and instead of actually creating something separate to do that, what we're going to do is we're going to subclass array. And we're going to have that array involved with many HTTP. And then it's going to process the results. And instead of just using a simple array and having some other process for that. So then they decided, well, that worked initially, but there's much of error handling in that. So they decided to throw that in there. Then they decided that they wanted to add additional options to query Solar, so they just tagged something really small. And then they decided, we're using this in a lot of different models throughout the application. So we're actually going to store our facet list up at the top, just constant of all these models. Then we're going to use metaprogramming as a tool to define all of these smooth methods, which I think this is a horrific use of metaprogramming. And then they decided, you know what, we're going to add a lot more queryable options. So they just kept tacking on all these small things, these small areas of complexity. And this thing over time grew very quickly. But it didn't just impact this code, it also impacted all the code that uses this code. And they got to the spot where they wanted to create something else in Solar. But this was slightly different. So they're like, hey, this worked well in this one case. So we're going to copy that same pattern and just reuse that for this other class. So all the complexity and complication from one area, they just ported over to another spot. And this doesn't only impact this class, but this is going to impact all the things that collaborate and interact with this class. But the software is not linear in the sense that you have one piece of complication that it only introduces like a smidgen of complication to the entire system. At least that's not how it works. Software is more of a non-linear process. So like the top graph here is this is a bunch of complexity metrics we're going to reuse. Plenty of open source projects. And on the bottom, this looks at code change versus complexity change. So the red actually is the code change, and the blue is still the complexity. And you can see that sometimes you add a little bit of code and the complexity spike. Sometimes you remove a little bit of code and the complexity still spike. So the software is really more of a system that feeds back into itself. So the change that we make today is going to impact the change that we're going to make tomorrow. And the changes that we make aren't isolated in the sense that if you add one gross thing here that is completely isolated from the rest of the system, it won't impact anything else. What it's going to do is it's going to impact the caller of that code. And then if that introduces additional complexity, it's going to touch the callers of that code potentially. And it's kind of spider out. Another way to consider this is that a previous change impacts future changes. I'm assuming that some people here probably recognize this image. Anyone know what from? Cool. Thank you, back right. Send me that there.
We're the old part.
All right. But the one neat thing about Connor's game of life and the way that the images progress is this is completely dependent on the last position of where all the black squares go. And this is kind of similar to software. The change you're going to make is completely dependent on all of the black squares that you did before. And even though in the bottom right you get back to the same type of pattern, you're actually in a really good spot. this guy here is basically to show that you have 0.2 being used in this equation, and then you've got 0.2001. So minuscule differences. And initially, you don't even see the blue because the blue and the red are perfectly mapped on top of one another. But over time, as this function iterates, they separate, and the differences become magnified, become a lot bigger. And this is extremely similar to how I feel software developers. So we just start out with a certain set of processes or practices, or values or sets of disciplines. And initially, we can look like we're kind of working towards the same result, but at some point, it's going to be those minuscule differences that are going to determine whether or not this system becomes unmanageable at some point, or this system is going to be able to kind of happily be sustained in the All right, here's a celebrity photo. Ashley picture. Whoa, I heard something over here. Awesome. All right. Well, there are two guys. I'll give that two guys.
What was the answer?
The answer is the butterfly effect. So, which despite its great past and great story, like it's wonderful from scientists who made it. If you don't like reading about complexity, watch this. You guys are quicker than I thought. Alright, well, we're going to look out to that guy too. Alright, so kind of what we're building to those is the sensitivity to these initial conditions. And that's what we showed in the chart with the red and blue that started out mapping on top of each other, and then over time they make that farther apart. And this is this idea of being sensitive to initial conditions is kind of the colloquial term for chaos theory in a sense. That even though there's going to be seemingly random behavior, that really is very ordered, and it's not really that random at all. But it's also not very deterministic. And this poem, I think, eloquently kind of captures that. I'll just put it, for the want of a nail, the shoe was lost. For the want of the shoe, the horse was lost. Then the horse, you want that, but that's lost. That. And so on until you basically lost it. And I think that there's some correlation between like this thinking and how it works software. Like, you make these minuscule decisions at one point, but that's going to actually kind of have a trickle-down effect in a way that's going to impact the rest of our system. So day one, it's awesome, but day 60 sucks. And we're like, how do we get this? Because at day one, the decisions that we started to make. As we iterated over those decisions, let us not right. So this is the whole point of this talk. So in the 1980s, got Kurt Bach, Chao Tang, Kurt Weisenfeld. These guys are looking at like dynamical systems, which is really just a system that you can make a very small change, but it can have a very large impact. So microscopic changes have macroscopic effects. But they were looking at this, and they used the sandpile model to kind of see what happened right on that edge, that cusp between a microscopic change and a macroscopic effect. So their idea is basically that, from a fixed point above the place, you just drop grains of sand. So, everyone close your eyes. Free. Yeah, that's alright. Now imagine that you're dropping a grain of sand from a fixed point. Now, what happens as you continue to drop those grains of sand? I'll give another quick reference.
They have a pot.
Wait, say that again?
Make pot.
It does get in a pot.
They slide down the bench. They bounce.
Who said slide? Alright. Got it. I think this guy was the one I heard. Alright, so yeah. Your pile builds up, that's one thing. But also what happens is it landslides. And that's just as long as you continue to feed the sand pile model or the sand pile system by dropping grains of sand. It gets to a point and it's going to landslide. And kind of this property of the sand pile model, they coined as like self-organized criticality. And this is really just to say that a property of the system is that this critical point, this point of landsliding, that is actually a natural part of the system. As long as you continue to add stuff to it, it's going to naturally get tracked to that point. Another way to look at it is that systems can only sustain so much stress. And a landslide in the sand pile model is a way to reduce that stress. The system by itself it has a way to reduce that stress. It never sets it back completely to zero, but it removes it in some extent away from that critical point. And then as you keep feeding the system, of course, it gets closer to that critical point until it has to reduce it. And that landslide is the macroscopic effect from that microscopic change. You're just adding a single grain of sand, and if it takes 100 times to create your first landslide, you don't do anything different on that 100th time than you've done for the first landslide. So you're repeating the same decision, the same process that you went about of adding things to the system. But at point 100, it seems like randomly something really bad happened. And then another way to look at this is that a trigger of any size can cause this large scale change. You don't have to make a really big change or a really complicated change to kind of make something bad happen. You can make a single small pointed change to make something very bad happen. Which makes it really hard for us as developers because it kind of shows that predicting is really difficult to do in software. We track iteration velocity on a lot of our projects. And iteration velocity, and I've never seen this, I've been at 3 companies over the last 10 years, I've never seen this actually be like completely linear to where you're always, or not linear, but constant, where you are always kind of, you're getting velocity of 20. It never works that way. Like, at some point you get like velocity of 45, and at one point you get like velocity of 3. And there's all of these things in there. And that makes predicting for us really difficult. So I was reading about the sand pile model, and it kind of connected with me in a way that other metaphors for software did not connect. They broke down too early. But this one actually connected, and I want to walk through why they connected with me. So adding functionality to the system is a bit like dropping a grain of sand. Adding a feature is like dropping multiple grains of sand. As we're adding things to the system, our system is naturally attracted to its own critical point. I think this is true for software in general. And the critical point in software, kind of mapping this model over to a software metaphor, is that the system is no longer in a state that can be easily added to as is. So it's in a really bad state. It's overly complicated. You have to stop making forward progress to kind of clean house. And this isn't, I'm not talking about cleaning as you go or refactoring as you go. I'm talking about kind of waiting for a mess and all this stuff. You're tracking all of this stuff. And the system, your velocity basically stops because you can't add more stuff to the system. So a really oversimplified example of this, if you take a monolithic program, you've got a single file, we're going to throw out classes and modules, and you just do functions and global variables, and everything's global. And so you start building the system in this file. And initially it's just really easy because there's nothing in there, so you can maneuver the code however you want. And then you continually add more stuff to it. And as you add more stuff, it gets increasingly more difficult to kind of maneuver around. At some point you get to a spot where you have to stop and you have to be like, whoa, I can't just add things in the way. We need to come up with some variable naming conventions, but we need to come up with something to kind of manage this growing complexity. And I think this is really oversimplified because we don't know this with monolithic files, and not everything is completely global. But I hope it kind of illustrates the point I'm trying to make, is that as you keep on tapping stuff, that complexity grows naturally, just because you're adding. And at some point, you have to stop. And monolithic programming is much sooner than maybe a couple hours. Whereas in a real system, it's going to take longer, but you're still also going to need to get a custom. So real software, though, is more interesting than dealing with like this fake monolithic program because it has more of everything. And real software is really kind of a series of like sand piles and sand boxes. You never just add stuff to one part of the system. You you have the ability to add stuff all over parts of the system. So you're kind of building all of these pods throughout your system. So in this visual here, there's really small piles, there's some bigger piles, there's one jagged pile in the back, right? You know, that there are different parts of the system and they have their own kind of amount of complexity associated with them. And for anything interesting that we do, there's always going to be some complexity. When there's zero, you know, in a system that has no complexity, there would be like no sand because there would nothing happen. That's awesome. So the teams they get caught up by starting out at this really rapid pace, and then they get halted afterwards. I've experienced this. I've observed this, and this is something that maybe catches some of you. Is that the first 60 days are awesome, and then after 60 days, so it's like it's a completely different piece. Because essentially what happens is you move this ginormous pile just hacking stuff up. But the problem is when this baby decides, that's going to touch like every part of the system. That like isn't overflow the same box. It's going to touch every part of the system. Or you go the other route, and maybe you've got not just one giant sandbox, but you've got all of these like kind of jagged peaks throughout your system. So like everything is at near its critical point to where the next thing you add is a very high likelihood of kind of being a tipping point and causing you to kind of landslide your system and go through and clean a bunch of stuff up. Maybe you weren't planning on working on it, but to get the change in there that you need to get in there, you got to go touch this part. And by touching that, oh, you got to go touch another part. And by touching that, and this is kind of like a cascading landslide. So my realization was that the simple act of adding something to the system moves the system closer to its critical point, its critical state. And this is like the software system's edge of chaos, so to speak. Just by going in there and adding anything, you are moving up towards that critical point. Unless you do something that's completely detracted away from it. But if you're not doing something that's completely detracted away from it, you're always moving your system towards that point. It could be a small change, you might not feel it today, but in 60 days, you keep making the same decisions, you might feel it. And then this is what happens. You find this like vicious stop and go cycle, where as you add functionality, the difficulty of adding new stuff to the system kind of goes up. And initially, you don't have to worry about it because the difficulty is really low. But then you get up to this critical point, and all of a sudden, like, this shit hits the fan, and so you have to do a little bit of cleaning house to be able to introduce another change, which is great. But you just do enough to keep moving. So then, very soon, you're back up to the same spot you were just in. So you make another minimal change to just keep moving. And then you get this vicious stop and go cycle. And the thing that kind of sucks about this is that there's this misconception associated with working that way. And that misconception is that you're being pragmatic because you got features out week 1, week 2, like, as soon as you could. So you think you're moving as fast as possible. But really, in the long term, because you're in this vicious stop and go, and you're at like the system in its most difficult state to add stuff all of the time, you're really moving at your slowest possible pace over the long term. But that's really hard unless you have a lot of experience getting bit by this. It's especially hard for when we work with apprentices or interns or new people who come in to work with us, or working with a team that has some kind of, I'll say, inexperienced developers, maybe just got out of college or whatever. They kind of fight against this because intuitively they want to move as fast as possible from day one. But they kind of do that at the cost of the long-term effects. So our truth, the part of this is like initially it requires more effort to avoid that critical point than to work towards it. And we also have to be conscious of that because intuitively, like our brains aren't going to think about that. Our brains are going to think about, I want to get this feature out right now, I want to get this thing out right now. So initially, it might actually be better off to take some time and to actually get in a set of practices or some kind of framework or set of conventions over the long term, you can keep your system in a really manageable state with the lowest amount of complexity as possible. And then the overall consistency easier to work with, you're actually moving long term at a much faster pace than if you went the other way around. But this is completely dependent on the size of your system. Because if you have a really small app, you might be done before you ever get to that critical point. Whereas if you have a larger app, you might hit that point for that thing. And just a brief sidetrack for story real quick. We were working with a client who had built up an internal team to kind of build a platform. And they worked with this internal team for a little over a year, probably about a year and a half. And initially, like the first several months, things were awesome, and they had no problems. But they hit this critical point, and then they brought us in, and we started working with them to kind of help them figure out what's going on with the system. But the entire system was messed. Like they were this vicious stop website where everything was just tacking on complexity, like barely cleaning anything, and then tacking on a bunch more complexity, barely cleaning anything. Whereas if they were done in the first 7 months of their project, and they had built like the main feature set, it wouldn't have been a problem. But they happened to hit it. And it's hard because we don't know exactly what the future entails for our software, how big it's going to be, what these requirements is. So it's kind of, luck of the draw almost, if you're learning to stop before you hit that critical point. Or if you're going to have to go through a vicious stop moves. But this, the vicious stop and go stuff kind of happens because you build complexity on top of complexity on top of complexity on top of complexity, and then that branches out and touches another part of the system because maybe you've got a complex interface. Maybe it's seemingly easy because you're passing in a giant hash of options, but really that hash of options is kind of masquerading around as hiding all of these complex objects that you have to pass into. And then those things kind of branch out again. But when we add in this one piece of complexity, we never do the whole stack at once. We're just doing like one row there. It doesn't seem that bad. It seems like it's going to be negligible. And we can go clean it up. We'll clean it up later, right? But that never happens because the cleaning never goes as far as it needs to. And usually, once we finish something, if there's a sense of priority for getting this change in, there's probably going to be a sense of priority here. It's like, oh, that's done. Well, here's the next change. We need this next change just as quickly. So how do we keep software away from its own critical point? And when I was first creating a slide deck, I was thinking about all the practices and processes and things that you can do to kind of help with this. And from getting a little peer review, that was actually not the advice that I want to give. And then when Rich gave his talk, which I love Rich's talk, it kind of really hit home that it's not about the practices or processes that are served. So it's more about things like simplicity. Falling in love with simplicity. Loathing unnecessary complication. And I use the term complication here because complexity in itself is not inherently bad. Complexity is just the combination of multiple simple things kind of working together to make something. And that's not always a bad thing. But complication, that's a bad thing because that means something's overly complex. So in loving complication, you want to kind of champion complexity. And in the top Sam Powell model, as the system grows, there's a little bit of complexity at day 60. In the back, there's a little peak, but there's kind of some rounded hills. Rounded hills, in my view, one thing I like about the Sam Powell metaphors is like it's really easy to visually connect with because a really tall, steep sand pile that appears to be more complicated because it's closer on the edges. And it's like, whereas if you feel like a flat rounded surface, it doesn't seem to be. But then on the second one on the bottom, you see that by day 30 we've got all these little jagged peaks growing into by day 60 they're just huge. And if any of those landslide, they have the chance of kind of overflowing to other parts of the system. So briefly, I'll read the same example we saw earlier. They kind of added all of this responsibility to this overloaded inherited array. And this is actually something that we did in our system. Was we broke out the thing that made the HTTP request to Solar and had that communication into its own class. And then we moved this here and there. The response that was coming back was mostly JSON anyways. So just have a response object and it's like map that to JSON. And then we can just easily load up the code from JSON and pass it to JSON. And then if we wanted to, or when we went to actually go add more configuration options, we throw out like Solar query object. And the names are slightly different, but for sake of brevity, I kind of try to shorten them and not include some of the namespaces and such. But the Solar query object, that can handle taking all of the options and then making sure that those things are converted properly into what Solar expects. But then the rest of the code kind of stays the same. We update the Solar request to work with the query config object, but we don't have to change the rest of the code. And then rather than having this fast list that kind of loops over and dynamically creates all of these different singleton methods on our overload array, take an approach where we've got a simple class that takes a model class, and then we'll just move the code that we just saw into here. And this thing's responsible for kind of coordinating the effort of talking to Solar and then mapping and creating these records. But what's nice about that is we can actually just wrap a simple method in a module and then go to send those into our models. And the code in our models is actually it's very much more descriptive, intention revealing about what book does. So if you look at the book model, you see what it does, opposed to having to know that somewhere in some Solar record set array, this thing's actually defining functionality for books. And then in the case of like having another class where they actually wanted to do a very similar thing, we don't need to copy and paste all these bad patterns. We can extend the module that we've made is reusable. Or if we're going to overload something, maybe we just write a class method on some other class. Under our options are what we're going to do, and then we can reuse the class that actually goes to most of this. Now, in this is just one example, I think, of where we've actually managed some of the complexity. Like we've got talk to the parts of the system and have to process Solar results and build models, but did it in a way that kind of distributed that responsibility to different objects. And all of those things now are kind of testable in isolation. They're easy to understand. If you go into look to see how the Solar requests are made, you don't have to load up all of this knowledge about everything else that is there, which again goes to one of the points that Rich made last night. Our method capacity is certainly minimizing hitting that is in our favor. But a lot of this has to do with just listening and kind of feeling and responding and learning from all the feedback that we have along the way. And all of these things combined is really values over practices. If you're actively seeking ways to exploit your values might be different than mine, slightly might be different than yours. But if we're actively seeking to exploit our values and the things that we do, like the practices are going to come as a natural part of it. And this is going to be reflected in the way that we go about developing software. An example of why I say values over practices. I've seen a lot of people who move a bunch of controller logic and they just basically cut and paste it down in the model, and that's refactoring to them. But that's a really bad refactoring, in my opinion. But I've seen a bunch of other people who do other things where they actually go identify concepts in the code and they try to spell out responsibilities, and they make it really easy for the system really easy to work with. And that's a good refactoring. So the practice is the same, but the values behind it kind of are driving where we end up. And the same thing for ready tests. I'm a huge fan of testing in general. I'm not a TDD zealot. There are times where I enjoy test first, but there are times where I also just enjoy to write code and then test afterwards. But there's this misconception that you can take a complicated code and you can just slap a test on it. And I've seen a lot of tests like this. And those are really scary to work because it's just another giant mess of complexity that someone has to do with this. But this kind of applies to pretty much anything that we do, any of the practices, tools, processes that we use in developing software. If it's not being driven by some value that we see, then there's a really good chance that we're going to do it wrong anyways, or that we're not going to get the maximum benefit out of it. So whether practices are important, or practices are important, but the values are kind of, those are the things that are part of the practice, and those are things that determine the decisions they make. So whether they're plentiful or lacking, it's the values that's going to impact every practice they make. I don't find the reverse of that to be true. And then pulling this back into the same problem before. As we iterate and build our software over and over again, it's going to be those values that drive how fast the difficulty and complexity of the system is going to take us at every point. And values help determine how we drop our grains of sand and where we drop it. Are we going to put it all in a single file and just, application controller, get ginormous, the 500 methods that you want to share throughout everything? Or are you going to actually identify a different part of the sandbox that plan and start distributing some of the complexity so that you can remove unnecessary stuff and simplify the complexity? Okay. I added this after Rich's talk last night of just pushing elephants. At some point, the system's going to get to a point where it doesn't matter how good your process is, or the tools you're using, the methodology you're using. If your system is to be a ginormous power, it's not really going to matter much in terms of pushing that. So this idea though that all of the, or that any change that we make can actually kind of put our system over the edge. It can be tough for some people to swallow. But I think it's just a natural part of developing software. And as you add anything to the system, you make it more complicated. So it's not just about tacking something on, it's about tacking something on in a minimal way. So I think if we can afford ourselves the humility to accept this, I think we'll be better served as kind of curators and caretakers of our systems, much like kind of gardeners with their gardens. And I left out some slides that I want to briefly touch on. I've got 5 minutes left. Is collecting metrics. I don't know if people here use CodeClimate or people here run their own metric collecting stuff. That's back to CodeClimate. Those projects are awesome, and we need more of them. I know there's Ruby that's out there, which if you haven't looked at Ruby, I hope it gets picked up and maintained by someone. There's a few tweaks to make to work with 1.9. But the way they have that set up is really easy to go add in metrics. But metrics and visualization tools of metrics, I think, will lead us to a great place where we can actually find new patterns in the way that we're going about developing software. The git log analysis, if you go back from day one of commit on master all the way to wherever you are now and run on complexity metrics against every single commit, and then go chart those out, go graph those out, there are a lot of interesting patterns that seem to happen. And there's giant complexity spikes and giant complexity reductions. You can go look at those points and go find out why did this spike, why did this not spike. But anyways, I'll end with this, kind of how's the landscape of your guys' software and what's it going to look like. So that is Sam Powell's software. There's an April article in Prag Pub on the same topic as this. Well, thank you guys for coming. So I hope you enjoyed the talk.